Let's go back to the questions that I always like to frame when I think about thermodynamics and kinetics. I like to frame my thinking around these questions. Why do we care about thermodynamics and kinetics? Well, because we care about whether the reaction will happen or not. So that's where we care about delta G, and we care if it's positive or negative, because that will tell us if the reaction is going to happen or not. We care about whether the reaction will absorb or release heat. Will we need to heat it up, or will it just give us heat? And that's where we talk about endothermic and exothermic reactions, and we care about this. And all this is thermodynamics. And then we also care about how fast will it happen. So it's not enough to know will it release heat or absorb heat, will be spontaneous. We want it to happen when we want it to happen. A few minutes, a few hours, a few weeks, a few years. We want to control how long it's going to take for the reagents to make our products. And we want to be able to make them go faster or slower, depending on if it's a beneficial reaction or not. And remember, I mentioned the case of CFCs destroying ozone layer. So we want to be able to control the speed, the reaction rate. And this is the domain of kinetics. And the last thing we care about is what can we do if the reaction gets stuck? If, despite the fact that we still have reagents, so you would hope that they would make products, they actually don't. Or better said, they keep making the products, but now you have so much product that instead of reacting with each other to give you back the reagents. How do you do that? And we call that equilibrium. We say that our reaction has reached the equilibrium. And in a thermodynamic sense, we define this as delta G is 0. So delta G negative number, smaller than 0, that reaction is spontaneous. Delta G positive, larger than 0, the reaction is non-spontaneous. If you want it to happen, you need to do something about it. It will not happen spontaneously. Delta G 0 means it's spontaneous and not spontaneous at the same time. It means it has reached what we call equilibrium. We will see in the next slides that all reactions have the potential to reach equilibrium. Some of them reach it easier than others. Okay, let's try to visualize this in a graph. Let's imagine we have a reaction in which you have a reagent A that forms a product B. And we're going to draw a diagram of reaction rate versus time. So initially, it's very commonly reagents start very enthusiastically because you have a lot of reagents, so there are lots of collisions and lots of molecules of your reagent colliding with each other, and some of those collisions are more likely to be effective and more likely to yield the product. So you have a high reaction rate because you have a lot of reagent still in the mixture, and you form the product, and the speed in which the reagent reacts is the speed in which the product is formed. At some point, you start having less and less reagents, so that means less and less efficient collisions because you have fewer molecules of a reagent, and that the amount of product, the amount of reagent being broken down into product slows down, so the amount of reagent being formed again slows down. If that reagent and product have nowhere to go, if your vessel is completely sealed, if they just stay there, at some point you have a lot of product and not much reagent. So the collisions between the reagent molecules start beginning to be less likely, and the ones that you have, not all of them are going to be effective, and you start having a lot of product that starts colliding with each other, and some of those collisions will be effective. And what will they give you? They will give you back your reagent, which is where they come from. So suddenly you start having molecules of reagent that react to make product, and molecules of product that react with each other to give you reagent. And at some point, you have sufficient reagent and sufficient product that both rates, the one of the reagent making the product and the one the product making the reagent, stabilize in a particular value. And you get something like this. They might meet, they might cross, whatever, but they become stable. They are the rate they meet. I should maybe have drawn them slightly closer to each other. They meet. The amount, the speed at which the reagent is being broken down to make the product is the same speed as to which the product breaks down to make the reagent. This point where both lines meet is called the equilibrium point. From that point onward, you end up in what is called a dynamic equilibrium. Both reaction rates, backwards and forwards, are the same. And the reaction reaches a standstill. You cannot make more product, because the product is reacting back to give you a reagent. Any reaction will reach that if it's in an enclosed environment. So in a closed reaction vessel, if there's nowhere for that product to go away. Because if it goes away, or you can remove it, or for example, if it's a solution and it precipitates as a solid, anything that gets it out of the way will allow the reagent, yes, you will have less of it, yes, this reaction rate might slow down, but you will still make product, because the product will not be there colliding with each other. So if a reaction vessel is shut, is locked, if you don't remove the product in some way, if the product stays, you will always reach an equilibrium point. In many cases, even if the reaction is not happening in an enclosed reaction vessel, for many reactions, you will reach that equilibrium point, even if it's in the open air, even in theory the product could go anywhere. And that is when you have a product which is more stable than the reagent, but not much more. So then the products start reacting back to give you the reagent. We have seen this type of equilibrium, for example, if you think of acid-base chemistry, a weak acid. And the difference between a weak acid and a strong acid. And I think I talked about, for example, hydrochloric acid, HCl, decomposes in water to give you hydrogen ions and chloride ions. And that's a strong acid. And those products, the hydrogen ion, the chloride ion, are much more stable than the hydrochloric acid. So the reaction stays like that. But if you have something like acetic acid or carbonic acid, we gave several examples, then yes, the products are more stable than the reagents, and that's why you make them. But at some point, when you have sufficient products, they're actually not that much more stable, and they react back to give you the reagent. So all the reactions will reach equilibrium if they are in a closed vessel and the product has nowhere to go, because you will beat a certain amount of product that will kick in that conditions to make the reagent. And even if it's not an enclosed vessel, in some cases, some reactions reach that point more easily than others. And we have, for example, that's what happens with weak acids. The products are not much more stable than the reagents, so when you have a certain amount of product in the solution, those ions react back to give you the reagent. And that's what we call a dynamic equilibrium. It's not that reaction is not happening, it is happening all the time, non-stop, it hasn't stopped. It's just that the rate forward and the rate backwards are the same. You are breaking product as fast as you are making it. And you can define what we call an equilibrium constant. And it's a constant that gives you an indication of the ratio of reagents to products. And the equilibrium constant is something measured, you measure it, and this is how it's defined. If you imagine you have a reaction A plus B, that gives you the compounds C and D, and they have certain coefficients. That I'm going to use the small letters of those letters to define. So you have a reaction with two reagents A and B, and with particular coefficients that give you two products C and D. The equilibrium constant that you will have to measure in the lab, well, this tabulated, but they are measured in the lab. They are not a model or anything. That's something you measure. Would be the concentration of the products. So the products are C and D to the power of whichever coefficients they've got, divided by the concentration of the reagents, the product of the concentration of reagents, again to the whatever coefficients they've got. So that equilibrium constant, that number, relates the concentration of the products and the reagents when the equilibrium has been reached. So a large equilibrium constant means you generate a lot of product, and a small one, you generate little product. So, yes, a large equilibrium constant means you have generated more product for that reaction in that condition. It depends on temperature. So the equilibrium constants change with respect to what reaction you're looking at. They are different because you have different chemicals, and they also depend on the temperature. They are given at a particular temperature, and if you don't specify the temperature, just assume it's room temperature. So it gives you the proportion of reagents to products to reagents, and that in that equilibrium, in that moment in which the reaction going forwards and the reaction going backwards are at the same rate.